Okay, here we go. Welcome to the next session. We have three presentations. Our first one is the paper Quadratic Modelings of Syndrome Decoding by Alessio Caminata, Ryan Carter, Alessio Meneghetti, Rocco Mora, and the speaker, Alex Pellegrini.
Thank you very much for the introduction. Yeah, as you said, it's a collaboration with Alessio Caminata, Ryan Carter, Alessio Meneghetti, and Rocco Mora, where we worked on giving some quadratic modelings, so an algebraic perspective of the syndrome decoding problem. So we tried to give a new point of view or a different point of view than the usual combinatoric word of attacks to the syndrome decoding problem, which underlies basically the security of many code-based crypto system. So let me start by giving some definitions in the coding world. So for me, Q is a power of a prime, and an NK linear code C is a k-dimensional subspace of FQN, where FQ is a finite field with Q elements. Okay. The support of a vector in FQN is the set of all the positions in the vector that are non-zero. Okay, and from that we can define the Hamming weight of a vector x of length n by taking the cardinality of the support of x. Can you hear me? Is it good? Very good. And we have that H is a parity check matrix of C if C is the right kernel of H. Okay? Good. So with this definition, we can describe the problem that we are tackling. Actually, Hiroki before he already defined them. So the first problem is the syndrome decoding problem over FQ, which reads as follows: given a parity check matrix H, n minus k times n, and a syndrome S, which is a vector over FQ of length n minus k, and an integer, non-negative integer t, we need to find a vector x such that H times x transpose is equal to the syndrome transpose. And the Hamming weight of x has to be at most t. There is a specialization of this problem, which is called exact weight syndrome decoding problem. We call it like this, actually, over FQ, which basically asks that the weight of the vector must be exactly t. Okay, this is very randomic. So in this talk, I will talk about two contributions in our paper. One is an improvement over a pre-existing modeling of the syndrome decoding problem, but over F2. So that work was modeling the syndrome decoding problem over the binary field. And the second contribution is a new modeling of the syndrome decoding problem over FQ, so any field, any finite field. So let me describe shortly how the previous work was made. So I set L to be the logarithm of n just for notation simplicity, and we are working over the polynomial ring F2 big X, where big X is basically a set of variables n plus n times L. Okay, and the idea is to build a set of polynomials or equations as follows. So first we take linear equations from the parity check constraint and the syndrome. And then we use n extra block of L equations each. These equations, they have higher degree, not quadratic, and each they involve L fresh variables, okay? And these equations here, they are made up to compute the weight of a solution of the point one. I cannot do it. A solution of this part of the system, okay? Then there is another extra equation that enforces that the weight that we just computed is at most t, and also this equation has higher degree, up to L. And then finally we add field equations in order to have all the solutions of the system living over F2. Good. So let me show you how this system is built. I don't want to give you the equations because they look very, very ugly. So I will try to explain a little bit how it works, how the equations are working in terms of defining the solutions of S. So if we take E v1 until Vn to be a solution of S, and we expand it, we have E to cover the first n coordinates, and then we have these n blocks of L coordinates each. The equations in the system are basically making the ith block of L coordinates to contain the binary expansion of the weight of the first part of n coordinates, the E part, up to the ith position, okay? So basically, the first block here is going to contain the binary expansion of the very first coordinate of E, so basically the projection of E to the first coordinate. The second one is going to contain the binary expansion of the Hamming weight of the first two coordinates, and so on and so forth, until the last one, which will contain the actual Hamming weight of the vector E, okay? Yeah, and the equation in step 3 is basically ensuring that the value represented by the binary expansion in the last part is at most t. So this sums up to n plus n times log n variables and equations, and they are, as I said, higher degree equations. So there is some sort of linearization process that comes in order to decrease the degree of the equations to 2, and this happens by introducing variables and some other equations which describe dependencies of these new variables, but this also adds log 2 factor into the asymptotic cost number of variables and equation. So the first improvement that, the improvement, the first contribution that we did was to improve this system, and we noticed that there was some kind of recursion, some kind of dependencies in the equation computing the partial weights. And with somewhat simple manipulation of this equation, it was possible to reduce all these equations down to quadratic. So there is no need of this sort of linearization process. And so we don't have to pay the log 2 cost when building the system. Then it's possible also to cut down further the number of variables and equations by just requiring that each partial weight must contain a value at most t, right? That's actually better, that can be done. And for the exact weight F2, we can also, so the exact weight syndrome decoding problem over F2, we can also turn the step 3, so the extra equation of high degree that checks that the actual weight is less or equal than t, we can turn it into L linear equations. Comparing it a little bit, in terms of asymptotic sizes, we have that we replaced the log 2 n squared, log n squared with log t, where t is at most n, and in most of the cryptographic application is much lower. And for the exact weight syndrome decoding problem over F2, we can find exactly the number of polynomials and variables, and we also have a quadratic system of equation. Very good. So let's go to with the second contribution, which is a modeling of the syndrome decoding problem over FQ. We start with two integers, R1 and R2. The R1 is going to define basically an extension field where we are working on. And yeah, R2 is adjusting a little bit the number of variables and equations that are going to appear in the new system. So X, Y, and Z are again blocks of variables. Y is somehow two-dimensional blocks of variables where each big Y1, big Yn are vectors of variables, or tuples of variables. And the idea is still the same, that each Y1, Yn is going to contain partial weights of the solution, okay? Again, we build a system of equation over FQR1 in X, Y, and Z, where X models the candidate solution of the syndrome decoding problem, so the system of the solutions of the parity check matrix and the syndrome. Z now captures the support of a solution, okay, somehow. And then we are modeling the Hamming weight of this solution by bounding the Hamming weight of the support, okay? So if we denote X, Y, and Y1 until Yn and z a solution of S, this is what happens to the solution, to the system. So first we take the n minus k linear equations in X given by the parity check matrix and the syndrome, as before, exactly the same. And then we compute the 2n quadratic polynomials in X and Z, which are given by these two sets of equations. Okay, the second set is just saying that all the Z variables have to live over F2. And the first one is saying that Zj has to be 1 anytime that Xj is 1. But it doesn't say anything about when Xj is 0, right? So this ensures that the support of the Z part of the coordinates of a solution contains the support of the X part. So the actual solution to the syndrome decoding problem. In other words, we have that the Hamming weight of the Z part of the coordinates is larger than X. So now we just have to bound the weight of Z, right? And we have a binary vector, not anymore a vector over FQ. So how do we do this? Assume, let's take a primitive univariate polynomial over FQ to the R1, of degree R2. Here is where R2 comes into play. And a companion matrix of F is given by this matrix CF, where we have the identity down in the left corner, a 0 row, and then we have a column with all the additive inverses of the coefficients of the polynomial. These are R2 times R2 matrix. And then we set Y0 to be the vector of length R2, with 1 at the first position and no zeros after. So basically now, an LFSR with update matrix CF initialized with this state produces a sequence of length Q to the R1 times R2 minus 1, okay? And the idea now is to replace that counter, that binary counter that was in the previous modeling with LFSR states as a weight counter. And we need this condition in order to capture the right solutions. I mean, otherwise in the system we could get some solution that have higher weight and the LFSR is just wrapping around its own period, and we don't want it to count solutions which have higher weight than T. Okay, to compute the weight of Z, now we compute the NR2 polynomials, which are quadratic or at most quadratic in Y and Z, which are given by the expansion of these two equations, or this set of equations and the first one. So the first one basically says that the first set of variables Y1, or the first set of coordinates in Y1 will be the starting state if Z1 is equal to 0, right? Indeed, the second part of the equation is going to cancel, and we have that Y1 will end up to be equal to the starting state. Otherwise, if Z1 is equal to 1, the LFSR is going to clock, basically, and we're going to the next state. Yeah, the second set of equation is basically a generalization for J starting from 2 until 2n. So we are going to clock whenever Zj is 1, and we're going to stay at the same state otherwise. And this basically ensures that the jth part of the counter contains a state of the LFSR which is dependent on the weight of the Z part of the coordinate up to the jth coordinate. And in particular, we have that the last part of the Yn contains exactly the state of the LFSR which corresponds to the weight of Z. Finally, we compute the R2 linear polynomials in Y from the expansion of this equation here, Yn minus Cf to the T. And combined with what I said before, by setting that Yn has to be that state dependent depending on the weight of Z, we have that the weight of Z is equal to T. And as I said before, the weight of X is also less or equal than Z, and this will make the job for defining or checking that the weight of x is less or equal than t in the system or in the solutions. And this sums up to a system of equation with this number of quadratic polynomials in n times R2 variables. And R2 is adjustable, so I mean it must be quasi-linear in n. So as a consideration, we have that we didn't put any field equations for x, which means that the modeling is quadratic so far, which is good. But on the other side, it actually models the syndrome decoding problem over the closure of the finite field, right? Unless S describes a zero-dimensional variety. In this case, then we have that it models the syndrome decoding problem over FQ, which is exactly what we want. So how is the variety described by S? So by describing, or breaking down the solution set of the syndrome decoding problem, we have that the solution set of the syndrome decoding problem is a finite union of affine linear spaces. And so we can relate the Kroll dimension of each irreducible component of this solution set. The Kroll dimension corresponds to the dimension of each irreducible component as an affine linear space. And also we have that for each of the solutions of the syndrome decoding problem, our system has a finite number of solutions, which doesn't increase the dimension of the variety. And therefore, it is given, I mean, we have a proposition with somewhat of a proof, and the dimension of the variety associated with the system is given by T, so the weight defined in the syndrome decoding problem, minus the minimum of the ranks of these matrices HI, where I is basically a set of indexes, and HI is a submatrix of the parity check matrix where we pick columns indexed by I. I is a subset of 1 until n of cardinality T. And these HI are such that when we augment the matrix with S, the rank doesn't change. Okay, when is this zero dimensional, right? That's what we want. Well, we have that for T smaller than n minus k, and WIC being the number of code words of weight exactly I in C. So with WIC is basically the weight distribution of C. Then it is given the probability of having a variety of which is positive dimensional is given by this formula here. And I have some examples here which says that when we take T going up to the Gilbert-Varshamov distance, which is defined down here, the probability of having a positive dimension variety is negligible. Okay, so almost always our system is gonna model the problem over FQ and not over the closure of FQ. So how do we solve a system of equation? We usually compute Grosvenor basis, right, of the ideal generated by the elements in the system. And the complexity of doing this is mainly given by this formula, this binomial with the matrix multiplication constant at the exponent. And we have that SD is the solving degree. How do we compute the solving degree? By computing Grosvenor basis usually, right? So we are getting into a loop. There is one way. How long do I have still? How much time? It's gone. Okay. So there's one way to bound this solving degree, which is given by the degree of regularity, which is defined like this for some sort of homogenization of the system, and which is often an upper bound on SD. We could compute it for the exact syndrome decoding problem over F2, which is given by this formula, but only for the fixed part of the system. And sadly, this is not a real good bound. It's a very coarse bound, as you can see here. The degree of regularity is much bigger and getting bigger and bigger with increasing length of the code. And instead, for FQ SDP, for the syndrome decoding problem over FQ, we gave some examples, and we tried to adjust the R1 and R2, so changing a little bit the size of the finding field we're to work on and the number of variables in the equation. And we can see that there are some choices that are really changing the solving degree. So some systems are actually better or easier to solve than others. And yeah, that's it. Sorry for for the long talk. Thank you very much.
Okay, so are there any questions? Okay, I can start. You said that if you have a zero-dimensional variety, then you're solving over or a zero-dimensional ideal, you're solving over the field FQ. Is there any hope of using this if that's not the case and still getting something better than just adding the field equations in?
You mean to shrink down and try to filter out the spurious solutions?
So basically get a Grosvenor basis without the field equations that possibly has things that don't reduce down to linear. So you have something that gives you a solution in an extension field, but is there some way of possibly getting that and mapping it back down to something useful in FQ?
I'm not sure about this. We tried to work on that. But I don't think we did any progress in that direction. I'm sure that I remember that we tried to work in different directions, trying to avoid putting field equations there. But we didn't find any way to really do it. So, yeah.
Okay.
I think it might be something to explore a little bit more in future. Yeah. But so far we didn't manage.
Also, how does this compare with the combinatorial approaches?
It does really bad.
It does really poorly.
Yeah, it does really bad.
Is there any hope for that? Is there a parameter regime in which it is competitive or might offer some benefit?
We did many experiments. No, there's not so much at the moment. We tried to apply some hybrid approach in computing Grosvenor basis or solving the system by fixing variables. I mean, many times you have that. Many times. Most of the times in cryptography, you have that the first part of the solution has very low weight, right? So you have only T positions that are set, and so you can try and fix some of the variables. But this is exactly the same of what information set decoding is doing, right? So yeah, we did some experiments doing this, and the complexity really converges there. I mean, it's the same approach because in the end, Grosvenor bases are really doing Gaussian elimination over the Macaulay matrix, right? And you're basically shrinking down the Macaulay matrix and you do Gaussian elimination. And yeah, it's basically the same what ISD is doing Gaussian elimination to find invertibility and then inverse them. So I don't know if there are like ad hoc, let's say, algorithms which are never very good, but for this kind of system has a lot of structure, as you can see, right? So I think there's a lot that can be done still to shrink down the solving degree, the degree of regularity, or use less variables. I mean, you can adjust here that R1 and R2 work over bigger fields and use less variables, or work on very small fields. I mean, depending on which algorithm for computing Grosvenor bases works better for you, you can adjust and say, okay, I need less variables because this is faster, but I'm working with a bigger field. So this is something that we could do in that direction.
All right, well, thank you. I think we need to move on to the next talk. So let's thank the speaker again.
Thank you very much.